Okay, so let us quickly review what we were doing in the discussing the joint stationarity. So basically, joint stationarity, the concept of joint stationary time series comes when you have more than one time series, bivariate time series or trivariate or multivariate time series, like what we have seen that Southern Oscillation Index and the recruitment of new fish, that new fish in the fishing, those series, two series, and they have a multiple seasonality, like multivariate seasonality, and those we could expect that if those time series is somewhat correlated. Okay, so naturally we will be in most of the real life scenario, in the most of the data science project, the time series data will be multivariable time series or multiple time series object. So we have to really understand the correlation between these series and whether we can meaningfully interpret those correlations. Now, if I have two series, X here and Y here, say they are said to be jointly stationary if each of them are stationary. So X itself stationary, Y itself stationary, and then one more condition you need, their cross covariance function is only function of only lag age. That means cross covariance function is not depending on the time itself. Okay, so how are you defining cross covariance function? Expectation of xt plus h minus mu x. The mu x is the mean of the x series, and yt, not t plus h, yt. So it's like my x at time point 1 and y at time point 3, say h is 2, so y 3, are they correlated, and is that correlation stationary or is that covariance stationary? So what I mean by that x, if the covariance at x1 and y3 and say x7 and y9, they are same, they're both of them are same, and of course it will only vary, it will be only function of h, the lag. That means x1 and y3, x1 and y5, we would expect to be varying over the lags. So that if that is happening, then we can say that cross covariance function is only function of lag and not depending on the time itself. Now, once you find the cross covariance function, finding the cross correlation is very easy. You just divide that by the variance of x and variance of y. So gamma x0 and gamma y0 is the variance of x and variance of y, and square root of that. So essentially standard deviation of x and standard deviation of the x time series and the y time series. And obviously you can argue that this correlation will be always between -1 and 1, and it will, depending on how are you taking xy or yx, obviously they will, if it is stationary, then they will be symmetric. The symmetric will hold if it is stationary, but if the symmetricity does not hold, you try it, you check it, you calculate the correlation between xy in lag age and xy in minus age, and if the symmetricity does not hold, that will be an indication that maybe correlations are not stationary. Okay, if they are stationary, then this symmetry will hold. Okay, so this is the example we discussed, that we tried, we took the WT and WT minus 1, WT plus WT minus 1, defined it as a X, and WT and minus WT minus 1 as Y, 2 time series. And what we found, that in the correlation, at lag 1 there is a correlation, but in lag 0 and lag 2 and more than 2 there is no correlation. So we can say that this is an operation on the white noise. White noise, every WT autocorrelation is 0 for everything, all the lags. But after this operation, you are inducing a correlation in the series. So why this learning is important? Because going forward we will do lots of operation. So this is a simple linear transformation, right? This is a simple linear transformation. So if you do a linear transformation on your time series data, that means it may change the correlation structure of your time series data. So simple example, we start with a white noise, which is completely, all the off diagonals are zeros, only the diagonals are sigma w square, because it's a completely independent and identicals. Then we did operations. As soon as we did the operation, lag ones are all now non-zeros. Okay, all rest of the off diagonals are zeros, but the lag 1 diagonals are all non-zero now. So that means if you do a operation on a time series, its correlation structure most likely will change. So every time you do an operation, or we will do an operation, we will be very careful about how the correlation structure is going to change, and if it changes, is it going to help us or it is going to create more problem for us. So we have to be cognizant of that structural change in the problem, in the problem statement. We discussed this problem, I think one of the cutest problem that I always keep saying, because it's a small tiny simple problem, but it also gives you an idea that how can you make your data science code much more overall efficient. That yt is equal to a xt minus l lag l plus omega t. Now omega t is white noise, and you are assuming omega t and xt minus l or xt, they are uncorrelated or they are independent. If you just make that assumption, now you want, so you are assuming it is sort of a regressions type structure between yt and xt, because a will behave as a coefficient and xt minus l is just a lagged value of the time series. You can always, so that, and why we are interested in that, if this model really good, then from this time point of x values I can forecast the y value, L lag ahead. Okay, so even if it's a small problem, small mathematical model, it's a very useful actually. I want to forecast y, say L step ahead. So what I will do, I will try to find another series x. If I find somehow that x and y, they are L lag highly correlated in by L lags, then from the, if I know what is the current value of x, then from there I will be able to say that L lag ahead, y's value will be somewhat this. Okay, so that's why this model, even if it's very simple, but actually is very useful. Okay. We will not be able to use this model all the time, but it is a good model to have it in our toolbox. Okay, now I want to figure out what is the autocovariance function and eventually cross covariance function. So actually, sorry, not autocovariance, the cross covariance function. Now if you look into the cross covariance function, what I will do, expectation of yt plus h minus expectation of y, which is 0, and times, because this is my autocovariance function definition. Now expectation of mu x and mu y is 0, then all I have xt plus h times yt. Same thing here in this problem. I have given expectation of xt equal to expectation of yt equal to 0. Now you can say it is a strong assumption. May not be, because I can always do a location shift. I can just take the average of the thing and then subtract the mean from all of them. So it will give me something like this. The transformed location shift transformed series will give me this. So it is not that bad actually. Now what is happening? I got this expectation yt plus h xt. Now a will, now you replace yt plus h by this guy, the right side of the equation. That will give you xt plus h minus l plus omega t. A is constant, going out of it, and then you apply expectation of xt plus h plus expectation of omega t plus h and xt. Now we are assuming omega t plus h and xt, they are uncorrelated, so this part is 0. So the second part is 0. I am left with this guy. Now what is this guy? This is auto covariance function of X series itself, h minus lag L length. So in order to calculate cross covariance, I don't have to write any function on cross covariance. All I have to do is just take the autocovariance function. If I just write a code to calculate autocovariance function of X series, multiply with A, I will get the cross covariance of the both series X and Y. Now, so that means basically you can reduce your coding effort, overall coding effort, and just simple matrix multiplication will give you the entire cross covariance function. Okay. Now in the book there are two different processes. If you go through the Shumway-Stoffer's book, they have talked about linear process and the Gaussian process. I feel at this level it is a bit complicated, so let's avoid that, and we will come back to this concept of linear process and Gaussian process later. Gaussian process, essentially we have introduced it in our regression classification course, but we will come back to that later. Now we have introduced all the theoretical concept of autocovariance, cross covariance, autocorrelation and cross correlation, but theory is not enough. We have to end of the day estimate these functions, estimate these parameters. Now theoretically it all sounds good, but end of the day I have only one time series to calculate the autocovariance function. I don't have millions of time series or something like that, like hundreds of replications of the same time series. So one time series is one observations, you can think in that way. I don't have the entire observation. So all you have the sample points x1, x2, xn, only these are the available to estimate mean, autocovariance, autocorrelation functions. Once you estimate the autocovariance, just take h equal to 0, that will give you the variance. the lag equal to 0 will give you the variance. So that's all. So all I am interested in calculating mean and autocovariance and the autocorrelation function. From the point of view of classical statistics or frequent statistics, this poses a problem, because we will typically not have IID copies of XT that are available for estimating the covariance and correlation. In the usual situation, with only one realization of the time series, the assumption of stationary T becomes critical. If we do not have the assumptions of stationary T, then we will not be able to estimate the parameters of the time series model. Okay. Yeah. So so far whatever probability statistics you have learned to estimate the mean parameters and the machine learning, every time you have assumed that your every sample are independent, at least independence, not the identical, may not be identical, but at least independence is required. Yeah, even Pearson correlation, whatever parameter you are estimating, even in the machine learning algorithms, pretty much we always, what we call instances are nothing but a sample. These instances are independent. We don't need to assume identical, but independence is the key assumption in all the estimation methods, so that we can write the likelihood and we can optimize the likelihood. So far whatever you have done. In the time series, at the very beginning we are saying that we don't know whether they are effectively independent or not. Most likely they are not. Most likely they are correlated. Each sample, x1, x2, most likely they are correlated. x2, x3 or x1, x3, most likely they are correlated. If they are correlated, then I cannot, when I am writing my likelihood, I cannot apply the product formula on my likelihood. Marginally, I can assume that each of the samples are realization from a Gaussian distribution, therefore their marginal distribution is Gaussian. I can assume that. But the problem is, since they are not independent, I cannot apply the product formula. Okay, for Gaussian, I know the multivariate thing, but as soon as multivariate version of the Gaussian, but as soon as I deviate from Gaussian, any other distribution, we simply do not know that multivariate version of that distribution most of the time, except few T and some specific version of gamma, like that. Most of the distribution we don't know multivariate version. So that is the problem that I am talking here. So in this situation, stationarity becomes a critical assumption. That is, stationarity is working perhaps. Now according to the stationary time series, I can say that mu t equal to mu. By definition, if the stationary time series is mu t, time series is a stationary, then mu t will be constant. So I don't have mu 1, mu 2, mu n. I have just one mu. And since I have just one mu, so most of the observations will be hovering around mu. So I can take the x bar as a possible estimator for mu. Clear? Now you can ask me, is it a unbiased estimator? Most likely not, as far as I remember, most likely not. It could have, is there a statistical consistency? Most likely yes. All these things are there. So yes, those are the valid intellectual questions, correct questions, but this is reasonable to use X bar to estimate mu if my series is stationary, because by definition, if my series is stationary, then mu t is constant mu. That means all my X values will hover around mu. It will not like go far away from mu, it will hover around mu. Sometimes it will be on the positive side of the mu, sometimes it's the left side of the mu, sometimes on the right side of the mu. So on an average it will give me, it could be biased estimator, it could be unbiased estimator, it could be statistically consistent or inconsistent. All these questions still are yet to be answered. But from a very common sense point of view, X bar, simple sample mean, could be a good estimator of the mean mu or mean function mu if my series is stationary. Now how I calculate sample covariance, autocovariance function? So all you do xt plus h minus x bar times xt minus x bar, sum them up from t equal to 1 to n minus h and divide that by 1 by n. So simple covariance function formula you apply. Same reason, you are hoping that your covariance function, autocovariance function, is only function of time and not only function of lag and not function of time. Same reason you can do that, because if it is not function of time and it is only function of lag, then it has its constant value, so the covariance will be around that value. So this is the same idea. So the theoretical autocovariance function is expectation of xt plus h minus mu times xt minus mu. So this is sort of a moment estimator. In all practical purpose, you can say it is a moment estimator. Now question is why I am going, the sum is running up to n minus h. We only have n observations. Correct. If it exceeds, then the first term will have a value which is xn plus 1, which we have not observed. Clear? So that's why the sum runs up to n minus h. Now the sample autocorrelation function is defined simply. You just take the gamma hat h. Once you have calculated it, then h equal to, you plug h equal to 0, you just divide that by the 0, gamma hat 0, that will give you the autocorrelation function. Effectively this is also product sample moments estimator for autocorrelation. Okay, because this is also a sample moment estimator and the top one is also sample moment estimator. So the whole thing is a sample moment estimator for autocorrelation. So then it will start from h, go up to n. That's it. If you just say t minus h, then your good question, you are interested in calculating xt minus h. Now in that case what you do, you just run from, instead of 1 to n minus h, you run it from h to n. That's it.
And that is equal to this H.
If it is covariant stationary, and if it is not, then you should be very careful immediately that maybe my covariance is not stationary, maybe it is a mean stationary, maybe it is a variance stationary, but it may not be the covariance stationary. A statistical mind should ask, can I develop a test for that? Okay? Right. So whether a time series is stationary or not, there are some tests. I'll come to that. Not today, maybe next week, on the Tuesday I'll come to that. But or maybe a little bit, because I may need to. But I'll just check. I may need to build little bit more theory to develop the test properly. But what is important, we do have basically statistical test to check if at least if a series is mean stationary or not, to check if a series is mean stationary. Okay. Once you have an estimator, this is an estimator, right? You'd like to know what is the sampling distribution of that, right? You'd like to know what is the sampling distribution of that, and unfortunately sampling distribution will be something very cumbersome. So what we have is a large sample approximation of the distribution of the ACF, and one of the special case of that approximation is if xt is white noise. Okay, xt does not have any information, all the xt's are independent, normal, 0, sigma square, blah blah blah. Then for very large n, the sample autocorrelation function for a white noise data, rho hat h, and h is the number of lag and capital H is the max lag that you are allowing, you can fix it arbitrary, slightly higher, is approximately normally distributed with mean 0 and standard deviation 1 by square root of n. So this result is known. Okay. So the result says if my underlying series X is a white noise, then the autocorrelation function will approximately follow normal distribution with normal 0, 1 over square root of n. Now this is an interesting fact. So now what I have done is how the white noise looks like, how the ACF of white noise looks like. I simulated xt, 100 xt from normal 0, 1. Now 1 by square root of n, n is 100, so square root of 100 is 10, so 1 by 10 is 0.1, 2 times of 0.1 is 0.2. So you can see there is a one bar is here, another bar is here. So my theory says most of my autocorrelation function values should be within the 2 standard deviation of this guy. I have simulated xt from normal 0, 1, so the autocorrelation values are all well within 2 standard deviation, barring this guy and this guy barely crossing the the compound. Okay. Now just for fun, I increase the sample size from 100 to 1000. Okay, same thing but 100 to 1000. my estimates of autocorrelation will be accordingly adjusted, and obviously because now I have more sample, my standard error bound or the confidence interval become tighter. Not confidence interval, rather say critical bound, because I am doing a sort of a test here that my rho h is 0 versus rho h is not 0. Now for a particular h, if that value is crossing the critical value in either side, if it is crossing the critical value either side, we reject the null, otherwise we don't reject the null. But here what we are seeing, again similar thing, except barring 1 and 2 here, most of them are staying well inside the critical band. Okay, so this is very assuring thing. Now I took the air passenger data and just plot the ACF. Certainly it is not white noise. So if you see a ACF like this, you will know immediately that your series is not a white noise. The series that you are looking at, it is not a white noise. It has something. Definitely strong signal is there. Let's do something. But when you get a series, look into the ACF plot, and if all the ACFs are somewhat like this, you know it's a white noise. उसमें कुछ है नहीं ना signal. There is no signal. It is completely garbage. Move on to the another series. Okay. Many of the stock markets, I keep giving examples from the stock market because one of my area of interest is computational finance. I have noticed that particularly the stocks which are very liquid in a very big company stock like IBM or Reliance or TCS, you take their return series and calculate the autocorrelation functions. Oftentimes they behave like that, like this. So that means basically they don't have any signal. They're completely random walk. They don't have any signal. And if you don't have any signal and if they're white noise, they're random walk, then anything you try, deep learning neural network, super deep learning neural network, massive deep learning neural network, you will only end up losing money. Nothing will happen because you don't have any signal. Then it is only telling you the story that you have some signal. What signal it is not telling you. It is a test whether I have a signal or not. If all my autocorrelation values are well within the band, it's telling me it has no signal. Bhai ye pura white noise hai. It is a complete white noise. Let's completely ignore my series. It nothing. I mean I will not even spend a single minute or second on that series at all because it's a white noise. But if it is like this, then for sure something is there. I will start investigating. If required, I will use. So sometimes people think like I am against deep learning neural network. No, I am not. Currently, I am running a project which is using massive deep learning neural network to solve certain problems. But what I am interested in is this data worth applying a deep learning neural network? Or is this data worth applying a Fourier transformation? That we must analyze critically. That is what I am trying to say. So here is another thing I have done. What I have done here, I have taken the air passenger data set and just took the consecutive differences. That's it. I have taken the consecutive differences. This gives me new series dyt, and plot the ACF plot of these consecutive differences. What I see, a very fascinating result, what I see that year 1, so it's a monthly data, and within, this is 1 year, 0 to 1.0 is 1 year. Within 1 year you have 12 observations. Okay, so lag here is slightly, so by 1 you should multiply it by 12, then you will get the correct lags here. But because the data was stored as a time series object, every 12 observation was considered as 1 lag. Okay, and it is annual data, so that is why it is showing 12 observation as 1 lag. But you can think, you have to, if you want exact lag 1, 2, 3, 4 like that, then you have to multiply the lag values by 12, then you will get the exact lags. Exact at year 1 there is a spike, then year 2 there is a huge spike, then year 3 huge spike. So it shows there is a very strong periodic behavior. So we can use ACF plot to identify a very strong periodicity. That every 12 months there is something happening. Now why I use this air passenger data? Because I knew that every 12 months something is happening. Now if I pretend I didn't know that, then this plot is helping me to identify that 12-month periodicity. Now your job is to take the sunplot data set. Sunspot data set, what we found that every 50 years, we have about 200 years of data, we have around 4 to 5 cycles, right? If there are 5 cycles, that means the periodicity is 10 years. If it is 4 cycles, then it is around 12 years. But we don't know which year. Is it a 10 year, 11 year or 12 year? Okay. So you can go and take the sunspot data set and try to identify the same thing. All you have to do, just take the consecutive differences, plot the ACF, and can you identify the main fundamental frequency that in every 10 year or 11 year, 12 years, you will see a spike. You should see the spike if this actually able to identify the periodicity. Yeah, Bhumika. Very good question. So, what do you think? So the question is it identifying the periodicity of the original series, or it is identifying the periodicity in the change in the consecutive change in the passenger pattern? Consecutive change in the pattern. Okay. What do you think? But it is also truth that there is a fundamental periodicity in 12 in the original series.
So is it like always true that if you plot the change difference, you will find the periodicity of the original series also? Or is this specific?
I don't know, and we will discover it. But I'll tell you one thing. If you go back, remember one thing, air passenger data set was highly non-stationary because it was constantly going up, right? because it's a non-stationary, so the ACF plot behaves very weird, right? Now you take the consecutive change, plot them, see how consecutive change of the data looks like. If I understand the problem correctly, my educated guess, I think the consecutive change series, this DYT, is a mean stationary process. Because now the data is being detrended, lot of trend related spurious correlation are now being removed from the data set. So there are two kind of the correlation here. The correlation between lag 1, lag 2 or lag 3 variables are due to two reasons. One is because of the trend and because of the periodicity. Now after taking the consecutive differences, the trend part is gone, right? If you take that consecutive differences, you can not necessarily it will happen. If it is a linear trend, one consecutive difference will remove your trend part. Then it becomes a mean stationary process. Now you have only the seasonality part. And that seasonality is getting picked up here. Make sense or not? Okay, so you have a homework. The homework is plot this DYT series, plot the air passenger series, plot the DYT series, which is a consecutive difference. My educated guess, because there is a linear trend, after taking the consecutive difference, it becomes mean zero process, means that the entire trend part is gone. So the correlation due to the trend is removed, and what you are left with is only the correlation due to the seasonality. And in that correlation due to the seasonality, the most strongest correlation is 12-month correlation, and that is getting reflected. Clear? Yeah, so all right, next is the speech signal that you have noticed. I just calculate the ACF plot of this speech signal. So you can see that in 100 hertz, I think somewhere in the 120 hertz, there is a very strong signal, but very difficult to make any sense out of it for me, because I'm really not an expert on speech data. So probably a voice engineer just looking at this plot may make sense out of it. So that is where domain expert working with when you're working as a data scientist, you need to work with the domain expert. Okay, and domain expert also need to understand a bit about how this autocorrelation function means, what it means. So, which is often very difficult to come by. If you are working with a voice engineer, they will understand. Generally, engineers do understand the math much better. But my experience is, if you are working with a domain expert who is from a non-science or non-STEM background, explaining the mathematical concept is much more difficult. Suppose you are working with a domain expert who is expert in, say, history or archaeology. In those kind of domain, it's much difficult. So here is the autocorrelation function of Southern Oscillation Index and recruitment data. So recruitment data was the number of fish that was recruited, if you remember. So you can again see Southern Oscillation Index is again it was a monthly data, and then you can see there is again a seasonality of 12-month seasonality is coming up very nicely. Okay. Then recruitment data behaves a very interesting way, which is it gradually goes down. It goes down at a 18 months level, it goes down to a negative level, and then it stays like that, and then on the 4th year there is some positive correlation. So again, how to interpret these things is a bit of a difficult, I think. So sometimes you will not be able to, it will not make much sense for you. But you only hope that this analysis will help you to identify a major fundamental frequency, a major fundamental pattern in your time series data, and you will be able to use these patterns to build a meaningful model. Okay. So these are the tools. I have not jumped into how to build a model, how to do the prediction forecast. Will come. Right now I'm just teaching you some tools to do an analysis of the data at hand, so that you can extract certain information from the data and then use that information to build a forecasting model, and then use that to build a good forecast. Now this is a interesting plot. This is a cross correlation function. This is a cross correlation function, and cross correlation function, autocorrelation function supposed to be symmetric, but cross correlation function does not necessarily symmetric. Okay. And if you have this kind of asymmetry, clearly there is asymmetry in my cross correlation function. That means one series is leading to another series. We will talk about it. We will do the hands-on. When we will do the hands-on, it will be much more clear to you. But what I mean by one series is leading to another series, because here a negative lag between one series and another series is significantly large, negative 0.6. This is not something you can completely ignore. These are stationary series. Remember that these are at least means, for sure mean stationary series, both the recruitment data and the SOI. And when we are looking at the cross correlation, lag H, so that means if it is a H 1.3, 1.4, maybe 3-4 lakh month of data of one value has a significant negative effect on another value. So if I know the particular value today or this month, 3-4 months down the lane, we know that the other value has a negative effect. But the opposite is not true, because I don't see the similar pattern here. Here is something, but this is not as strong as this one, near 0.2. But definitely this is something. Now, when we will do the hands-on, our interest will be, is the SOI, Southern Oscillation Index, affecting the, and recruitment data is the fish population. Is the Southern Oscillation Index affecting the fish population, or fish population is affecting the Southern Oscillation Index? This is what I want to figure out. If we find that Southern Oscillation Index is affecting the fish population, then we may have something in our hand. But if we found that fish population is affecting the Southern Oscillation Index, we may question it that maybe it is a spurious correlation, because really we don't want to say that fish population is going to affect how the what will be the temperature of and air pressure difference in the two position of the Southern Indian Ocean. So Southern Indian Ocean, so Southern Oscillation Index is typically estimated at in 2 point on the southern part of the Indian Ocean. I can't remember the exact point. If you just do the Wikipedia, yeah, and they take the air pressure difference, right? Now that might have an effect on the weather. So it is some sort of climatic feature that might have an effect on the fish population. But fish population probably not going to have an effect on the climatic or weather condition. So that's our idea. We will investigate it when we'll do the hands-on in the next lecture. So I'll stop here. Anybody have any question? So the other way around, most, as far as I remember, the Southern Oscillation Index, if I know the Southern Oscillation Index now, 3 months or 4 months down the road, fish population will be adversely affected or inversely affected. That was the idea of, that is the interpretation of this thing. The other side, even if they are sort of a positively correlated, but we don't want to say based on this that fish population is going to affect my weather condition. It may, I'm not saying it may affect. I mean, human activity, we now have a reason to believe human activity is going to affect the climate. So similarly, any other species activity may affect the human, like the climate. I'm not saying it cannot happen. You cannot completely ignore, because if, for example, if certain, I mean, it is still, I think it is a bit of a controversial question. I mean, whether, or it is not known. I would say, I would rather put it in as it is not known whether other than human activity, any other species growth. It might happen that, okay, one particular area of the ocean or one particular fish population or fish species is growing rapidly. Okay. Does it going to have a effect on the weather condition or the climatic condition or not? I have not seen any scientific report on this kind of study. So it might have or might not have. So it is, so this series, negative correlation, which tells us it's a significant, but can we say that, or is it a spurious correlation? That we have to take it with a carefully. We have to make that call. Which one? Let me. This one.
So, sir, in the cosmic correlation side, it is quite evident that we have a exact similar pattern.
This is right. What about this guy? This is what you were saying?
No, I am asking them in the first year.
The
The correlation absolutely The positive correlation is almost 1.
Almost no, no, it is 1 because it's a correlation with itself, no? Like lag 0 means correlation with itself, so it has to be 1.
So, in the it keeps on decreasing because of the lag increases.
Most likely.
Because there I can also see a linear decrease.
I mean, whether it's a linear decrease or non-linear decrease, that from this 4 year of data it is a bit difficult to say, but decreasing for sure, and most likely because the lag increasing.
And what about that question? What about the downside?
So
Quite similar.
correct. So it is like, because you have a sort of a Fourier behavior, like every 3 months if it is up, then after 3 months it was low, right? And then when it was low, then after 3 months it was high. So there is a negative association in every 3 to 4 months on a quarterly basis that is getting reflected, but it is not very strong. Why it is not very strong? Because there will be also a month which are 3 months apart, but right before the minimum, right after the minimum. So they will not be exactly negatively correlated or positively correlated, right? So that's why 3 month apart correlation or 4 month or 6 month apart correlation, they are somewhat correlated, like negatively correlated, but they are not very strong. But for sure 11, 12 and 13 months, like they are like really, really strong. All right, let's stop here today, and you are supposed to give me your homework.